Swayam Prabha. Digital India. Educated India.
Hi, and welcome to this lecture 7 of module 7. In the previous lectures, what we have been discussing is the ordinary differential equation initial value problem, and we have considered several methods, error analysis and stability analysis for these methods. So I will just go over and do a very quick recap on a PowerPoint slide and tell you what we are going to cover in the next 2 lectures. What we have covered so far is we started off with Euler's method, then we talked about in general about Runge-Kutta methods, made derivation for Runge-Kutta second order method, as well as saw the results for the fourth order Runge-Kutta method. We performed error analysis and saw that the truncation error for Euler's method was the accuracy is of the order h square. For the RK2 method, the accuracy is of the order of h cubed. For RK4 method, the accuracy is of the order of h to the power 5. All these accuracies that or errors that we talked about are in context of what is known as local truncation error, and I will come to that in the next slide. So we did error analysis for the Runge-Kutta family of methods, followed by the stability analysis. Then we took up a Yoon's method and put it in a predictor corrector form. As well as we considered explicit versus implicit methods. Specifically, we took the explicit Euler's method and implicit Euler's method and saw the stability results for a linear system. We compared a second order RK method with the Yoon's method, which is a predictor corrector method, and compared it with the Crank-Nicholson method, which is a semi-implicit method. And the final thing we covered in the previous lecture was extension to multivariate case. Specifically, we saw the Euler's methods extension to the multivariate case, and then we discussed how you can extend in a similar manner RK2 and RK4 methods as well. Those extensions are actually not just limited to RK type of methods. The same extension will work in any other type of method for ODE solving that we are going to consider so far. Okay. So that was what we have done so far in the first 6 lectures. In the next 2 lectures of this series, this is what we are going to consider. In this particular lecture, we are going to compare global versus local truncation error, and then we are going to cover 3 advanced topics in this lecture. So I will go over Richardson's extrapolation. Recall that Richardson's extrapolation is something that we had done when we were discussing integration techniques. So what we do is we will get h to the power nth accuracy solution and use Richardson extrapolation to get h to the power n plus 1 accurate solution. That is what we had seen in module 6 of this particular course, and how it would be extended to ODE initial value problem. We will talk about that today. More importantly, I am going to talk about what it means by adaptive step sizing, the similar kind of idea that is used in Richardson's extrapolation. A slight modification of that would be actually used in deciding the step size in the adaptive step sizing method. And finally, we are going to consider what is known as stiff ODEs. I will essentially define what stiff ODEs means and why the stiff ODEs cause numerical problems, and this is what we are going to cover. And finally, in the next lecture, we are going to cover Adam Moulton's family of methods, and that will essentially finish what I intend to do in ODE initial value problem module 7. Okay. So now let us go to this lecture. What I will do is I will again go to Microsoft Excel and pick up a sheet that we were using in the previous lecture. So let me just bring up Microsoft Excel over here. So this is the sheet that we were using in the previous lecture. What we wanted to solve is dc by dv equal to minus c to the power 1.25 divided by 2. This expression we obtained by deriving the design equation for a plug flow reactor. We start with initial concentration of the desired of the reactant as equal to 1, and starting with this initial concentration of 1, the actual concentration keeps decreasing as the time as the volume keeps increasing. So we had, what we had done is we had derived, or we had used this particular method for various different values of H. For H equal to 0.125, we had used this method, and what we had done is at volume equal to 5, we saw that the error was 10 to the power minus 7. What we did next was we changed H to H equal to 1, and for H equal to 1, the error in case of volume V equal to 5 was equal to 10 to the power, was of the order of 10 to the power minus 4. And with all these results, we had made error comparison between Euler's midpoint and RK4 method, and this error comparison is shown on this particular graph. All this we had done in 2 lectures earlier. Okay. So now what I am going to do is I am going to talk about what is known as local and global truncation errors. Okay. So we do not need any of this information, so I will just delete that, and I will just keep the values of V from 0 to 5. Okay. So what we did over here is we started with the initial condition at V equal to 0 and reached V equal to 5 over here. Okay. So now what I am going to do is I am going to take these 2 rows and then just paste them over here, and I will restart them. I will just color them with a different color, so we are able to see how these are actually going to be different. So I will just fill them with a yellow color over here, and I will redo these calculations for 4 equal to 4 and 5, and instead of using the approximate value over here, what I am going to do is I am going to use the real value of the true value of Ci plus 1 that we get. I am going to use that over here. Okay. And if I were to use the actual true value, so I will just copy this particular true value and paste that true value over here by putting paste values. Okay. Now what we see over here is, let us say we started off from V equal to 0 and we reached V equal to 5. Okay. When we did that, the error was 6 into 10 to the power minus 4. Okay. However, were we to start with the exact value of at V equal to 4 and then take one step to go on to V equal to 5, we will find that the error is significantly lower in this particular case. This error that we get is essentially the local truncation error, and this error that we have gotten is the global truncation error. Okay. So the difference is like this, is in the local truncation error, what we do is we assume that the previous value that we had was the actual true value. Okay. So the value at V equal to 4 was true value. If the value at V equal to 4 had been the true value, what would be the error at V equal to 4 plus H, that is V equal to 5. Okay. So if we started off with the true value, we will reach this particular value at V equal to 5, and in that particular case the difference between the true value at V equal to 5 and the numerically computed value at V equal to 5 is 6e minus 5. However, if we were to start at V equal to 0 and reach V equal to 5 through 5 steps, in that case the global truncation error is going to be 8 into 10 to the power minus 4, which is an order of magnitude higher than the local truncation error that we get over here. Okay. So that is the difference really between the global truncation error and the local truncation error. So I will just go back to the board and discuss a little bit more about global and local truncation errors. I will not do the derivation, but essentially give you the results for the Runge-Kutta family of methods. Okay, so what we saw in the Excel sheet right now just now is this, is we wanted to compute the value of concentration, how the value of concentration changes with the volume, okay, and we were interested in calculating the value of concentration at volume V equal to 5, okay, and I am going to blow up the differences between the numerical value and the actual value just so that we are able to see the what we really mean by the local and global truncation errors. So what we started off at V equal to 1, and the white line that I am showing over here, let that represent the true solution. Okay, so we started off at V equal to 1 and reached V equal to 0 and reached V equal to 5 in 5 steps. Okay, 1, 2, 3, 4 and 5. Okay, so this is how the true value goes. Now let us say that we use a numerical method, RK4 type of a numerical method, in order to compute the same values at 0, 1, 2, 3, 4 and 5. Now we are starting off again at the same concentration C equal to 1 at volume V equal to 0. Okay, we use the chosen method, say the RK4 method once, and from this particular point let us say that we reach this point over here. We apply the same RK4 method once again, and from this point we will reach this point to that I am showing over here. From this point onwards, if I apply this method again, I will reach here, I will from this point onwards I will reach here, and finally I reach this particular point. Okay, so if we take a magnifying glass and just blow this thing up, what we will see is we will see the curve coming like this and this purple cross over here. Okay, so this is the magnified view of this particular region. Okay, and this is the true solution. Okay, so what we do next is, let's say somehow this particular solution is available to us. If this solution is available to us, we restart our RK4 method at V equal to 4. We restart our RK4 method at the true value. Okay, so if we restart this RK4 method at the true value and run this RK4 method once, okay, then from this point, the next point that we get, the next numerical solution ends up being over here, this particular dot that I have shown. And when we blow up this particular picture, what we get is really that this dot ends up over here if we had started with the true value. Okay, so now if we were to calculate the errors in getting this purple dot, what this represents, this particular gap represents the local error in RK4. Okay, what that means is that the y I plus 1, the true value of y I plus 1 is equal to y I plus 1 from the RK4 method plus an error term which we can write as some constant C1 h to the power 5. Okay, so this error is proportional to the fifth power of the step size that I have chosen. Now this error is the local truncation error. This error is the error going from the ith value to I plus 1th value, assuming the ith value was the true value. So this represents the local error. Now when we started with C at V equal to 0, we went from C0 to C1, okay. So when we went from C0 to C1, there was a local truncation error associated with this value of C1, okay. So when we then go from this value, this numerical value to the next numerical value, there will be some error associated with the fact that the numerical method is not accurate. This has certain error itself, okay. There will be some other error associated because of propagation of this particular error, okay. So this error results in some of the error in the future step, okay, and there will be some error that will be caused because the numerical method itself is inaccurate, okay. So the effect of both these errors comes in the global truncation error, and this difference is going to be the global truncation error, okay. And this particular difference between the global truncation error and the local truncation error, this arises due to accumulation of past errors. Okay. So the global truncation error, we can say, is going to be some kind of a combination of the local truncation error plus accumulation of past errors. Okay, I do not mean this as an equation, I just mean this as a literal statement of fact, is that the global truncation error has a component of the local truncation error as well as component because of the propagation of the errors starting at the starting point and going to the desired point as for this numerical method. Okay. In general, what we had seen is for RK2 method, the local truncation error was of the order h to the power 3, the global truncation error will be of the order h to the power 2. Okay. For RK4 method, the local truncation error was h to the power 5, the global truncation error would be of h to the power 4. Okay. So for any RK method, what we actually get is for an RKN method, if the accuracy is h to the power m in the local truncation error, then the accuracy is going to be h to the power m minus 1 in terms of global truncation error. Okay. So the fourth order RK method is going to be h to the power 4 accurate in the global sense and not h to the power 5 accurate as we had derived in the previous lectures. Okay, what we had derived in the previous lectures is the local truncation error, which does not consider the fact that as we propagate into the future or into the larger volumes, the effect of truncation error that have been accumulated in the past also affects the overall error in the system. Okay. So that is the difference mainly between the global truncation error and the local truncation error. Okay. So that is one part that I wanted to cover today. The next thing I will cover today is we will go on to a little bit more advanced topic. Really what I want to cover is adaptive step sizing, but before going to adaptive step sizing, we will look at Richardson's extrapolation. Okay. You will recall what we had done in Richardson's extrapolation in module 6 was we computed the integral for h we recomputed the integral for h by 2 and used these two integrals in order to compute a better value or a more accurate value of integral. So, and we had said I nu was going to be equal to 2 to the power n multiplied by IH by 2 minus IH divided by 2 to the power n minus 1. Okay. So, this is what we had derived in the previous module. We are essentially going to go over almost exact same derivation for Richardson's extrapolation in case of the Runge-Kutta methods or in case of ODE solution methods. Okay. So, the idea is this, is what we want to do is we want to get yi plus 1 as accurate as desired. What do we mean by as accurate as desired is that we need to define what tolerance value that we need. Okay. So, we need to define okay, and we will call this, as we have been doing in the past, we will call this as epsilon tol, that is the desired tolerance value or desired error value that we will give. Okay. Now, in Richardson's extrapolation, before going to and talking about this particular tolerance values and so on, we will go over this Richardson's extrapolation. The idea is this: the true value yi plus 1, the true value is going to be equal to yi, that is compute, or yi plus 1, which is computed numerically, plus some constant C1 multiplied by h to the power 5 for the RK4 method. Okay. This is what essentially we had written over here. I have just rewritten this particular equation over here. For RK4, we have the true value yi plus 1 bar equal to yi plus 1 plus C1 h to the power 5. Okay. What I will do is I will just modify this a little bit in line with what we had done over here, and I will put in bracket yi plus 1 h plus C1 h to the power 5. So, this is using the RK4 method once, going from yi to yi plus 1. Okay. This is what we get. Now, let us redo the same thing, going from yi to yi plus 1 in two steps. In this case, the step size is going to be h by 2. So, we will go from yi to yi plus half, and from yi plus half we will go to yi plus 1 computed with a step size of h by 2. Okay. So, this particular method, when we use this method, is going to be more accurate, as we have been seeing all throughout. This method is going to be more accurate in giving us the value of yi plus 1 compared to the method in which we are going to use one single step to go from yi to yi plus 1. Now, there will be error that is going to be associated with this particular step, as well as an error that is associated with this particular step. So, we will have our yi plus half bar is going to be equal to yi plus half plus C1 h by 2 to the power 5. Okay. So, this is going to be our true value of yi plus half. yi plus 1 bar is going to be equal to the value computed at yi plus 1 from this particular guy plus the error that we will get at yi plus 1. Okay. So, now this error is also going to propagate into the future. So, without going actually into any of the numerical complexities into this, I will write this yi plus 1 is going to be approximately of the form of yi plus 1 plus 2 times c1 h by 2 to the power 5. The first c1 h by 2 to the power 5 comes because of we go from yi to yi plus half. The second c1 h by 2 to the power 5 comes because of the local truncation error going from yi plus 1 to yi plus half to yi plus 1. Okay. So this is essentially how we will write our yi plus 1 when we go for the true value of yi plus 1 related to yi plus 1 computed by taking 2 steps. Okay. And because it is computed by taking 2 steps, I will put in the bracket yi plus 1 h by 2. Okay. As we had done before, we will multiply this particular equation by 2 to the power 4, not 2 to the power 5 but 2 to the power 4, just as we had done in the integration method. We will multiply it by 2 to the power 4 and then subtract this equation from this equation. So we will get 2 to the power 4 y I plus 1 equal to 2 to the power 4 multiplied by y I h by 2 plus c1 h to the power 5. So we had 2 times c1, we had 2 times c1 h by 2 to the power 5. When we multiplied this with 2 to the power 4, all this got cancelled away and we were left with c1 h to the power 5, and that is what I have written over here, as well as yi plus 1, I forgot the bar over here, is going to be yi computed with h plus c1 h to the power 5. Okay. And of course there are c2 h to the power 6, c3 h to the power 7 terms also, and so on over here, which are not going to get cancelled, because we will essentially have plus c2 h to the power 6 by 2, and here we will have c2 h to the power 6. This is the term that I had not written down earlier. Okay. And now when we subtract these two equations and then divide throughout by 2 to the power 4 minus 1, we are going to get yi plus 1 is going to be equal to 2 to the power 4 yi h by 2 minus yi h divided by 2 to the power 4 minus 1. Okay. So this is essentially what we are going to get. Okay. We can write this as 16 times yi plus 1, I should have here 16 times yi plus 1 h by 2. I can write this as 15 times yi plus 1 h by 2 minus plus yi plus 1 h by 2 minus yi plus 1 h divided by 15, and which we will be able to write it as yi plus 1 computed at h by 2 plus delta divided by 15, where delta is defined as the difference yi plus 1 h by 2 minus yi plus 1 h. Okay. And this is going to be our final result. Okay. And similar derivations can be done for the RK2 method also, and for RK2 method we are going to get, so for RK4 Now how this 15 comes in? It comes in 2 to the power 4 minus 1. Likewise this 3 comes in because it is going to be 2 to the power 2 minus 1. The exponent is the order of accuracy minus 1. The local truncation error is h to the power 5 accurate over here, h to the power 3 accurate over here. So the exponent for 2 is going to be 1 less than the local truncation error accuracy. So it is 2 to the power 2 minus 1, that becomes 3, and the overall accuracy of this method increases by 1 order. So it is increased by from h cubed to h to the power 4. Okay, and this is for the RK2 method, this is for the RK4 method that we get. Okay, so these are the results of Richardson's extrapolation. Now the idea is this particular difference delta, okay, this in Richardson's extrapolation was used in order to improve the accuracy of the RK method and go to a more accurate method. However, this delta says something about the true error that we might expect to have in this particular system. So the new topic we are going to tackle is adaptive step sizing. Okay, so y I plus 1 bar is y I plus 1 computed with h plus c1 h to the power 5. Y I plus 1 bar is going to be equal to y I plus 1 computed at h by 2 plus 2 times c1 h to the power 5 divided by h by 2 to the power 5. Okay, so when we take the difference between these two, we will get 0 is equal to delta plus h to the power 5 c1 by 2 to the power 4 minus c1. Okay, so what we have done is we have subtracted this equation from this equation. These two are the true values and therefore the difference is going to be 0. The difference between these two values is going to be equal to delta, and the difference between these two values is going to be some constant multiplied by h to the power 5. Okay, so we take this particular equation on to the other side, and we can, so this is going to be 1 by 16 minus 1, take it to the other side, will become 1 minus 1 by 16 or 15 by 16. So we can write this as delta is going to be, the estimate of the delta is going to be h to the power 5 multiplied by 15 c1 by 16, or it's some constant this of this particular form. This particular value is constant and it depends essentially on yi and yi plus 1 based on the mean value theorem, and the exact value we will not have an estimate of unless the true solution is exactly known. But what this says is that the delta, that is the difference between these two guys, is proportional to h to the power 5. Okay, so delta is some other constant c multiplied by h to the power 5. C could be 15 c1 divided by 16 if you want to write it that way. So this is the value of delta. This is the estimate of this particular difference delta. Now if h was the step size, this is going to be the delta that we get. So delta nu for another h nu is also going to be c multiplied by h nu to the power 5. Okay, so if we were to change h from the actual value of h to a new value of h nu, this delta will change from this true delta to the delta nu. Okay, now we can basically divide this particular equation by this equation, and what we are going to get is delta nu divided by delta is h nu divided by h to the power 5, okay. And we can just rearrange this and we can write this as h nu equal to h multiplied by delta nu divided by delta to the power 1 by 5, okay. So what this equation says is okay. So if we change from h to h nu, the difference between a more accurate method and the less accurate method is going to change from delta to delta nu, okay. So now if we, instead of choosing this the delta nu arbitrarily, if we choose that delta nu equal to the tolerance value, okay, then the h nu that we are going to get is the step size that will help us in reaching that particular tolerance value, okay. So what we are going to write over here is that h nu is going to be h multiplied by epsilon tolerance divided by delta to the power 1 by 5, okay. So what we mean by that is we can go back to this particular schematic that we had drawn for the RK4 method, is if this particular error is not acceptable to us, okay, what we need first is we do not know the true solution. So we need a method to find out, to estimate what this particular error is going to be. So what we will do is, in addition to running this particular method using this step size, we will also run this method using the h by 2 step size, okay, and we will get this red crosses using h by 2, okay. This guy is delta. Now if this delta is acceptable to us, we keep the same h. If this delta is not acceptable to us, we are going to change that h. How we are going to change that h? We are going to scale that h in this particular manner. It depends on the tolerance value divided by delta to the power 1 by 5. That 5 comes in because the this method is accurate to the order of h to the power 5, okay. So if this delta is too large, what we are actually going to do is we will shrink the step size. If the delta is much larger than the epsilon tolerance, if delta is larger than the epsilon tolerance, what is going to happen is this number is going to be less than 1. If this number is less than 1, h is going to shrink a little bit. So what is going to happen next is, instead of taking a full step h of this form, we will then decide to take a shorter step h. So instead of going all the way over here, we will decide our h is going to be this much, and what we will do is, from this point to this point we will want to take a step of h. Again we repeat this adaptive step sizing once again. What we will do is we will take this particular h and redo this by taking 2 steps, and those 2 steps are shown as circles. Again we will compute this delta. Again, if this delta is not good enough, we will take a smaller step than the step that we had taken previously. As a result of this, we will keep adapting the steps as we go on further along this particular curve, okay. This is what is going to be an adaptive step sizing. Where is adaptive step sizing useful? Useful in lot of example. Let me just give you one particular example where it is going to be useful. If this is that particular device, okay, there will be a flame that stands over here. So it could be a lighter, it could be a candle, and if you start plotting the temperatures along this particular direction, you will get the temperatures to be fairly cool over here, and then the temperature will start rising, and then the temperature will shoot up, and the temperature will again fall, because there is a lot of heat loss taking place beyond this flame. For example, if this is candle and we put hand over here, we do not feel too much heat of candle because the heat has all dissipated throughout. Okay. So now if we want to make a model for this system and then run an RK4 method with adaptive step sizing on a curve of this sort, what happens is that there's the slope is very low in this particular region. So in this particular region, what the adaptive step sizing will do is it will take fairly large steps. So it might take possibly say 3 steps to reach over here. Now a lot is happening in this particular region. As a result of this, the things are changing quite rapidly. So the slope at this point is drastically different than slope at this point. So if we are going to keep using the same large step sizes in this region also, we will miss the overall physical characteristics that we see over here. As a result, the adaptive step sizing is going to take multiple number of steps in this particular region. Okay. Now the overall curve is tending to become smoother. Because the curve tends to become smoother, the step sizes will increase. Okay. And this is how we are going to get if we were to use adaptive step sizing. Okay. So H over here are large, in this region H's are small. Okay. In this region H sizes will be medium, and finally in this region the sizes of H will be large again. Okay. So what happens is, in the region where a lot of things are gradients are changing quite rapidly, you have many more steps taken. Okay. And this is what the adaptive step sizing method is going to do for our system. Okay. So that is essentially about the adaptive step sizing. Okay. So let us consider dy1 by dt equal to minus 1000 multiplied by y1. What this means is that this particular lambda value is very large. As a result, this system is going to respond very quickly. For example, if we were to plot y1 against t, it's going to respond in this fashion. The time scale for the time scale tau is going to be 1 divided by lambda. So the time scale is going to be equal to 10 to the power minus 3. So in approximately 5 milliseconds, the system would have gone from whatever initial condition it was to 0 in about 5 milliseconds. So this is going to be 0, this is going to be 0.001, 0.002 and so on, and this is 0.005. Okay. So this is what this particular system is going to respond. Now let us consider another system. Okay. Now this particular system is again qualitatively the response curve is going to look like this itself. However, the times at which we get a curve of this sort is going to be 0, 1000, 2000 and so on, and this is going to be 5000. Okay. So this particular system responds very quickly, this particular system responds very slowly. Okay. Now let us say that we were to solve this by Euler's method. Okay. For solving this by Euler's explicit method, in this particular case we would have to take h of the order of say 10 to the power minus 3 or 10 to the power minus 4 in order to get stable solution, and in order to get stable solution with a fair amount of accuracy. Okay. Whereas in this particular case, if we take the step size of 10 to the power minus 4, we need to run this particular method up to time 5000. As a result, the number of steps with h equal to 10 to the power minus 4 for this particular system is going to be equal to approximately equal to 5 into 10 to the power minus 7. Okay. Now we do not want to take so many steps for this method. As a result, the h for this system we will take of the order of 10 to the power minus 1. Okay. So this, if this was only one equation that we had to solve, we will take this h equal to 10 to the power minus 4. If this was the only one equation that we wanted to solve, sorry, not h to the power minus 1, it should be h to the power 3 minus 1, which is h to the power 2. That is the, sorry, 10 to the power 2. So that is the h that we will use for this particular system. So if this system and this system were to be solved independently, we did not have any issues, we can choose two different values of h, we can solve them independently, and that is the end of it. Now however, if we had an equation of the form d by dt y1 y2 equal to minus 1000 0 0 minus 0.001 y1 y2. Okay. So what happens over here is that y1 and y2 have very different time scales. Okay. So y1 and y2 evolve at very different time scales compared to each other. Y1 is evolving in about 5 milliseconds, whereas y2 is evolving over a period of an hour. Now the question is, what is the value of h we are going to take? If we take the value of h equal to 10 to the power minus 4, okay, we will end up taking the, we will end up requiring almost 5 million steps in order to reach the solution at time t equal to 5000. If we take h of the order of 10 to the power 2, this particular method is going to go unstable. Okay. So because of this stiff system of ODEs, the definition of the stiff system essentially is that stiff system is one in which there are components which have very widely varying time scales of evolution. Okay. So if you have a multivariable system, you can take you can differentiate the system and get this particular guy over here, find the eigenvalues of this particular matrix, the ratio between the absolute value of the highest eigenvalue divided by the absolute value of the lowest eigenvalue is going to give you how much stiff this particular system is. If this eigenvalue divided by this eigenvalue is of the order of 10 to the power 4 or 5 or higher, in that particular case the system is going to be fairly stiff and we will need to use stiff solvers. Okay. So for this particular system, the evolution, the way it is going to happen is like this. If we were to plot y1 y2 versus t, okay, y1, if t we look at up to 5000 steps, what is going to happen is that y2 will evolve in this particular manner, whereas y1 is going to look like this. It is going to look like it is a vertical line and a horizontal line. If we zoom into this particular region, okay, if we zoom into this region, this is what we are going to get, that y1 does evolve, but it evolves in 0.005 times and not in 5000 times, and in this small zoomed out period, if we were to look at this particular part in the zoomed out period, what we are going to see is that y2 is more or less constant. It is not even going to have this slope, it is going to be more or less constant in this particular time scale. Okay. Now this type of problems create a fair number of numerical difficulties, and that is because we need a small step size for stability of this method, whereas we need a large step size so that we have the overall solution reaching the steady state fast enough. Okay. Now Euler's explicit method or any of the explicit method is going to have a problem used in stiff systems, because it is going to require very small steps as governed by this the fastest mode of the system. So what do we do is the solution for the stiff ODEs is to use implicit methods so that we do not have to worry about the stability of these methods at all, we only have to worry about the accuracy of the system. In order to get more accurate solution in this initial region, we can have, through the adaptive step sizing, we can have a lot of steps taken in this particular region, and in the rest of the region we can actually take much larger steps, so that both the evolution of y1 as well as evolution of y2 we will be able to predict fairly well. Now the problem is why we require an implicit method and not an explicit method is, even if we take with an explicit method, if we use adaptive step sizing over here, the solution would not have gone to 0 in the finite amount of time. So when we start taking larger step size, what is going to happen is that the solution is going to be unstable. Okay. The reason why we cannot use explicit method is for h greater than 10 to the power minus 3 or 2 into 10 to the power minus 3, this equation is going to go unstable. So we cannot use a larger step size because as governed by this equation, and if we take a smaller step size as governed by this particular equation, we are going to take a very large number of steps in order to reach the final value. Okay. So this is essentially it, all I wanted to talk about the stiff system of ODEs. We finish off the lecture over here. What we have done is we started off with talking about the global and local truncation error, saw the where the genesis of global and local truncation error comes about. Then we talked about the Richardson's extrapolation method in order to get more accurate solution. The Richardson's extrapolation method depended on the difference between the error using a more accurate method and a less accurate method. That difference then we said can be used in this adaptive step sizing type of an idea, where we change the step size based on the difference between yi plus 1 computed with h by 2 as the step size and yi plus 1 computed with h as the step size. That is what we do in adaptive step sizing. And finally we talked about stiff system of ODEs, and stiff system of ODEs are the systems where we have multiple time scales occurring in the same system. These systems might be linear or non-linear. Non-linearity typically makes the problem even more worse than in the linear system, but stiffness is independent of linearity or non-linearity. It is independent of the actual values of y1 and y2. It depends only on what are the time scales at which y1 and y2 evolve. And finally we said that the explicit methods are going to be not very useful when we are going to use when we are trying to solve stiff system of ODEs, and we have to use implicit methods. So that is where I end this lecture today. Thank you.